Okay, we can start now. 12 minutes, right?
Okay.
All right.
Alright, well, good morning, Dr. G, and for those of you that may be watching, today I want to talk about my project on induced seismicity in the central region of the United States, specifically focusing on the state of Oklahoma. So quickly, I would like to just go through the trends that have been seen in the state. From 1960 to 2007, there was less than 1 magnitude 3 earthquake in this region a year. In just 2015 alone, there was 920 of these, which equate to 2.5 of these earthquakes a day. So scientists and industry professionals have all agreed that this is not due to natural causes, but is in fact caused by induced seismicity. So what is induced seismicity? Well, earthquakes naturally are a phenomenon in which plates are rubbing against each other either horizontally or vertically. So in places like California, where it's known to have a high earthquake rate, it's because of the oceanic plate dipping below the continental plate, and as that stress builds up, it can trigger a massive earthquake. But in Oklahoma, it does not. It's not located in between fault zones like this. It actually has faults within the crystalline basement itself. So in Oklahoma, it's actually surpassed California for the frequency and magnitude of earthquakes that have been happening recently. And this has been due to induced seismicity, as I've said before. So these activities can induce earthquakes through a number of ways. They can add pressure to existing fault lines that are already there. The water can seep into these fault lines, which may lubricate the surfaces and decrease the coefficient of static friction, or just by putting water in reservoirs above a fault zone, it may have enough load there to trigger the faults to move. And it's important in regions like Oklahoma because the fault lines that are there are nearly vertical, which is very optimal for earthquakes to slip, because there's not enough normal force in preventing that motion. So here's the mechanistic equation for this approach. The variables are outlined below, and as you can see from this equation, there's a number of ways in which these variables can play a role. So if you reduce the normal stress, or if you increase the shear stress and increase the pore pressure, these can all make the shear stress, the critical shear stress, reach failure. Once the shear stress hits the critical level, the fault will slip and the earthquake will propagate as the rocks release the stored elastic energy, and this elastic energy will radiate as seismic waves and will continue until the static strength of the underlying rocks over the given area exceeds the applied strength. So this can also be seen in the Moore's diagram. As the pore pressure increases or decreases, it triggers it to move right or left and can approach the failure line. So in Oklahoma, this is the diagram of the geology that's found there. Usually what is happening in the oil and gas industry is they're extracting oil through these producing layers here, and they may use it through the enhanced oil recovery well, which is a type of class 2 injection well. And this is able to increase the productivity of the amount of oil that's coming out of there, and it accounts for about 80% of the injection wells that are in the area. Now, when they take this water out, about 1 barrel of oil equates to 20 barrels of produced water. So there's an incredible environmental concern with this briny salt water that they cannot release it back to the surface. They have to inject it back into the ground. So what they do is they use a saltwater disposal well to inject it into what is called the Arbuckle Formation. Now this Arbuckle Formation is under pressured, and it's incredibly permeable, so for engineers it is thought to be a prime place for it to go in without causing disruption to the environment and to the freshwater sources. However, since it is incredibly permeable and it's just one layer above the crystalline basement, a lot of this water is seeping through the crystalline basement and is triggering the faults, as I've mentioned before. So the Oklahoma government website has already admitted that this has been a problem, and from their website I was able to gather this data. So here are the locations of injection wells through the Oklahoma region, and if you look at the earthquakes from just 2016 alone, there's a high correlability for what is happening here. So as the dots get bigger, obviously the magnitude of the earthquake is bigger and it radiates to a larger surface. So this giant red dot here was actually a 5.1 that happened a month ago, and it has caused a lot of damage. So some of the damage that it's been causing, back in 2011, the region was hit with their highest earthquake at that time, which was a 5.7, with a 4.8 and two 4.8 aftershock and foreshocks. And as you can see, it's taking down the brick mortar and the chimneys that are in the area. This area was not originally designed for something of these magnitudes. So either the chimneys can fall into their yard, or unluckily for this lady, the bricks fell into the roof of her house and has caused incredible damage. And about a month ago, this 5.7 earthquake that was a previous record was it was overpassed by 5.8, and it has made this tribunal historic area where you could see an inch between the two walls were moved apart, and the chimney was about to collapse too. It's all twisted and deformed, but this whole building is going to have to be torn down, which was a historic building. So one of the major concerns about this area is the city of Cushing in Oklahoma. So Cushing is known to be the pipeline's crossroad of the world. It's a major transportation and storage hub, and it accounts for a huge part of our oil infrastructure. The capacity for this field is 80 million barrels of oil, and about a month ago it experienced a 5.0 magnitude earthquake. And the downtown area was completely devastated, shattered windows, buildings had to be closed and torn down. But luckily for this oil field, there was no significant damage and there was no environmental hazard. However, it doesn't mean that it can't be in the future. So what I wanted to do is I wanted to look at what's the probability of this happening and causing a huge disaster. So I used some of these equations from our textbook in class. And I knew that the Wayzata fault zone, the Whitetail fault line, was 5 kilometers from research, and this fault line runs through that oil field as well as the Cushing airport. And so using this equation, I was able to find the probable magnitude that can occur there, which is about a 6.3, and that equates to about 113 joules of energy, and the maximum amplitude of acceleration on the ground was a 0.61 Gs. This was proven in the United States Geological Survey report, which was incredible because this report was the first time that they actually accounted for induced seismicity in the region. As you can see from the report in 2015, when they didn't, there's a huge difference in the peak ground accelerations that can likely happen in this area. Also in this report it shows what the MMI scale would be, which approaches above 7 in areas like Cushing. However, from our textbook, it needs an intensity scale of 9, which equates to a magnitude 7 earthquake for underground pipes to break. So therefore I can conclude that Cushing doesn't really seem like it could be an area of potential natural disaster. However, some of the old buildings, the central buildings that are there, they're not designed for this, and it should be accounted for rehabilitation and for future designs in the area. One ways that we can come together and take a proactive approach is to look more in depth about the fault lines that are there, maybe do some tests to see if we can gather the current state of stress in the area as well as the pore pressures. Right now the Oklahoma Corporation Commission is doing a traffic light approach, which is a very reactive approach. So if they have an earthquake, they're able to have the real-time data, look at how much the injection is and the probabilities that that injection well was to the triggered earthquake, but that only happens after an earthquake occurs. So I believe that this project would help in the benefiting for a proactive approach, and it should be looked at for something that is definitely going to happen, especially in third world countries where they don't have the type of structural strength that we do. These type of magnitude earthquakes can cause a lot of damage, as I've written in my report, but I don't have time to talk about today. So if you have any questions, thank you.
Good. So, I have a couple of questions.
Mm-hmm.
So you said that You need a magnitude 9 earthquake. In Richter scale, magnitude
A
9?
magnitude 7 earthquake.
7 earthquake
in
on,
the Richter scale,
on,
yeah.
on the Richter scale.
The intensity scale would be
Yeah.
intensity 9.
Right, that's the italic letters, right?
Yeah,
Those
yeah,
are okay. So magnitude 7 for a pipe to break. Well, I think some pipes can probably break for 5 magnitude earthquakes, depending on the structural integrity, right?
I would believe so, yeah, but it really depends on the design. I mean, I'm sure
Yeah.
that since it's such a massive oil infrastructure that they didn't take light ways around it, I'm sure they designed it to meet these kind of standards.
Mhm. And also, in the class you might have noted that the acceleration that is induced, the force that can be induced at a particular point depends on the soil mass also. Remember the gamma equation, right?
Right.
So, it depends on how much soil is there also, right? The acceleration is starting from bedrock.
Well, yeah. Well, the thing is, this isn't really happening at a deep level. The Arbuckle Formation is about 6 kilometers underneath, so there's really not that, compared to other regions. There's really not that much of an effect from the soil underlying layers.
What I'm trying to say is that if the pipeline, let's say a pipeline is laid through bedrock, I mean right next to bedrock, right? So as opposed to a pipeline, one pipeline is laid right across, next to bedrock, or let's say embedded in bedrock. I don't know whether they drill bedrock to lay pipelines, but assume, as opposed to a pipeline that is going through soil, overburden, right?
Right.
For the same magnitude of an earthquake, what do you think of the vulnerability of the two pipelines? Which one would break?
I believe the one in the basement rock would break.
Why?
Because that's where the earthquake is propagating from. Therefore, there's not enough of a damp loss of energy occurring compared to the one that's going to be above.
In terms of the maximum acceleration or the energy level, at least it's more intense. The vibration could be more intense, but at the same time the constraints are higher also, right?
Yeah.
Whereas in a soil, it can deform much more, and sometimes things can break, right, due to deformation.
Yes, this is true.
So what I'm trying to say is that it's a very difficult problem to solve. So I have some issue with the people who say that for a pipeline to break, you should have a magnitude 7 earthquake or something. I think it has to be, that statement has to be qualified with other statements as well.
Right.
That's the only thing. But apart from that, why is a layman's question, right? Why are they not talking about Oklahoma's earthquakes in newspapers and television and things like that?
Is this something you want to put on a video? There's a lot of politics behind it. It's a huge industry. Like I've said before, the industry accounts for 22% of the state taxable income in Oklahoma. So it's really not something that really wants to be talked about, especially since the oil and gas industry is kind of blowing up in recent times.
But if people's houses are getting damaged,
the thing is that these houses aren't being damaged in urban areas. They're being damaged in populations of less than 3,000 people that don't really have much of a say. So
you think so?
Yeah.
Or maybe they can be repaired easily, or
in Prague and Pani, which was the cities of magnitude 5.7 and 5.8.
Right.
Both of these cities had 2,300 people or less. So it's really not much of a concern unless it was going to strike, let's say, the Cushing Airport, the Cushing oil field, or even Oklahoma City, which has a population of 600,000.
So why did you select this project? Why did you specifically select Oklahoma? Look at Oklahoma.
I thought it was a very interesting trend, and like you said,
is.
not a lot of people are talking about it. So I kind of wanted to be the one to bring it up and see what I can find out about the area.
Okay, you can off it now. Off the record.